Okay, so last time we were talking about parametric curves and derivatives of parametric curves, right? So a parametric curve gives you position as a function of time. So as time passes, this thing moves along. If it's moving, it's got a velocity. And it turns out that this formula, our old familiar formula from Calc 1, right, that at the time, in that context, because we were looking at graphs in Calc 1, this formula gave us slope. But here, since we're not looking at a graph, we do not get the slope of this parametric curve, but we get something else that's interesting. This definition of a derivative gives us velocity. Right? So again, now also kind of a familiar result from Calc 1. I mean, this sort of the asterisk minor application that gets discussed a little bit in Calc 1 classes is that, oh yeah, in addition to slopes, it's also velocities if you have a car driving along a road. Something like that. But it's a relatively sort of minor observation. Okay, how do you compute derivatives? In Calc 1, we have a bunch of rules. Product rule, chain rule, quotient rule, etc. Right? I mean, do we have a bunch of rules for computing the derivative of a parametric curve? What does it mean to multiply two parametric curves? And is there a corresponding product rule? Right? You have this sneaking fear that, oh my gosh, I'm going to have to develop all new rules. Fortunately, you don't. Derivative of a parametric curve can be computed component-wise. Just take the derivatives of the individual components. And notice that the individual components, that x by itself as a function of t is a good old, plain old Calc 1 single variable function. And all the, Calc 1 derivative rules, they all apply because, of course, it is a Calc 1 function. So this component-wise calculation is a big deal. It's something that tends to get taken for granted a little bit too much. But anyway, very important that this is true. Okay, some algebraic properties of derivatives. And again, this tends to be a big yawn because, like, oh, come on, didn't we already know all this stuff? And I have to remind you, no, we didn't know any of this before right now. The sum of two parametric curves, right? What is that? That's not a Calc 1 concept, right? So, and likewise, this derivative of a parametric curve, that's a brand new idea, right? It wasn't what we thought it would be on the last page in terms of geometric interpretation. How do we know the algebra is going to work the same? Not at all obvious. Good news that it does behave algebraically exactly how we would hope. So, right, that was a close one. Notice here we kind of have two product rules. This is a little bit weird, but it's hard to imagine where this is going to come up. But it does, by the way. But why would you take the dot product of position of one parametric curve and then dot that with position of another parametric curve? It's really hard to imagine where this would come up, but it does. Anyway, the dot product rule of derivatives is exactly what you would guess. Likewise for cross products, pretty surprising, really, if you think about it, but also true. And likewise for scalar vector products, it's exactly the product rule that you would sort of expect. Okay. All right, so let's talk about antiderivatives, and I emphasize now antiderivatives, not integrals. By the way, if you're not really, really sure that you know the difference between an integral and an antiderivative, come talk to me. It's a big deal. It's very important. It gets swept under the rug a lot in Calc 1 classes, but it's an important difference. So by antiderivative, I mean really the easiest of those concepts is just kind of undo the derivative. Antiderivative is exactly what it sounds like. Okay. So good news, because derivatives are done one component at a time. No surprise, so are antiderivatives. So if you know velocity, keep in mind velocity is the derivative of position. Well, then position is the antiderivative of velocity. Antiderivatives, of course, always come with a little plus c. Again, remember the idea here is that what we need is that when I take the derivative of this equation, I need to get back to the original equation, and the derivative of that constant is 0, right? So, okay. So because this is true, that's true, and because it's computed component-wise, Here's how you actually do that. If someone gives you velocity as a function of, vector-valued velocity as a function of time, we take the antiderivative one component at a time, and that gives you position. Okay. Now, what about integrals? Right? What is an integral of a parametric curve? Well, you can write this down. That's true. Now, by the way, I want to make sure everybody remembers from Calc 1 that an integral is defined as a Riemann sum. Okay. Common mistake that people make is to think that integrals are antiderivatives. They're not. It's a very important difference. Come to my office hours if you're not 100% sure that you are clear on this. So integrals are defined with Riemann sums. Oh, another common mistake. People think that integrals are defined as area under the curve. Also not true. That's an application. It's not a definition. And it would be a really bad definition for reasons that I would be happy to explain in office hours. Anyway, this is all Calc 1 stuff. I want to make sure everyone's comfortable with this, but don't underestimate the importance of these points. So integrals are defined with Riemann sums, and so you might say, okay, well, I guess this is the Riemann sum that I would define for an integral of a parametric curve. So this must mean something natural and reasonable, and let's try to figure out what that is. But no, it doesn't. So let me try to persuade you that this doesn't mean anything interesting as I have it written down here right now. Because look at what we're computing. And by the way, always make sure, the devil's in the details. So make sure to look at exactly what it is that you've got and think it through as to what this should represent. What should it mean to take a position vector and multiply it by the amount of time that you're staying in that general vicinity? What is that? That's not a thing, right? That does not relate to anything that I can think of physically, right? So it's a very, very common mistake for students to think, oh, this must be, I guess that's area under the parametric curve. Maybe, like there's a curtain hanging down off of you've got this parametric curve going around in space, and there's this curtain hanging down, and what's the area of the curtain? No, absolutely not. That's not what this is. And in fact, again, this is not really anything that's particularly naturally meaningful. Okay, so heads up on that. Now, you still do have a fundamental theorem of calculus, right? If, for whatever reason, you're interested in an integral of a vector-valued function, let me put an asterisk on that comment. We'll come back to that in a moment. If you are interested in, one of these, for whatever reason, it is true that an antiderivative will allow you to compute that. And that's true fact. Why do we care? So the why we care comes up in thinking about situations where we know that this happens. And specifically, here's the situation we know where this happens. If this is position, then this is velocity. And what this turns into is an assertion that an integral of velocity gives you a change in position. Right, and that makes sense. And furthermore, if you, extend that, let's just take that a little bit further to, keep in mind we're viewing the thing that we're taking an integral of. Here, let me come up here like this. The thing that we're taking an integral of is velocity. If you were to go in here and replace x with v, notice that now you do get something that's pretty reasonable to talk about, right? It all of a sudden makes perfect sense to talk about taking a velocity and multiplying that by a time. Velocity times time gives you displacement. This is a natural thing, right? This summation of little micro displacement, summation of differential displacements should give you total displacement. So it all fits together. It all makes sense if you interpret it this way, right? But critically, in order for any of this to make any sense, notice we're not taking an integral of a parametric curve. We're taking an integral of a vector-valued function that is the velocity of a parametric curve. Then it makes sense. Right? But the integral of the parametric curve by itself, I don't know what's that. That doesn't even. I guess I can't imagine why anyone would ever be interested in that object. All right. Okay. All right. So y'all have seen these kinds of problems in Calc 1 classes. I'm going to go through this really quickly because it's the same thing pretty much. Suppose you are given acceleration and you're also given a starting velocity and a starting position. From this information, find position as a function of time. So y'all have done problems like this in Calc 1 classes with cars driving down roads. Right? So now this is just a two-dimensional version of that. Now acceleration is a vector-valued function. Right? Your initial velocity is a vector. Your initial position is a vector. And we're just going to do the vector version of this. And it's just one component at a time, right? Remember we talked about on the last page, antiderivatives are computed one component at a time. So it's almost like as we do this problem, we're going to be doing kind of two separate questions sort of in parallel. It's like, well, we start off with the second derivative of the x-coordinate being cosine t, and the initial rate of change is 1, and the initial value is 3. And then the second derivative of the y-coordinate is that, with an initial rate of change of that and an initial value of that. So there's a blue question and there's a green question. And we just kind of going to work them out in parallel, in effect. Okay. Anyway, that's one way to think about it. So, but here we go. Velocity is the antiderivative of acceleration. Easy antiderivatives, one component at a time. Wait a minute, what's this constant here? Now, don't make the standard mistake. The classic blunder is for students to think that constant's always the initial value. But it's not. The reason students mistakenly think that is when in a lot of high school classes anyway, when they write down the functions that are in here, they make them polynomials, in which case their antiderivatives all have at least one factor of t, and you plug in t equals 0, and this expression always ends up being all 0, in which case, coincidentally, weird coincidence, the integration constant ends up being the initial velocity, right? But that is a peculiarity of the severe limitation on those kind of examples of always polynomials. So in the real world, that is absolutely not true. Now, the way you get this resolved is we say, okay, let's consider t equals 0. And when t is equal to 0, velocity is equal to, keep in mind, t is equal to 0. That turns out to be that. And then we can solve for what we're interested in, right? This constant here, you can solve for. A little bit of arithmetic. Right, so we're just plugging in. And notice, again, very importantly, this not equal to that. Everybody happy? Okay, so now with this known, now we know velocity as a function of time, and then repeat, same idea, another antiderivative, another integration constant, another, plug in t equals 0, find the constant, and then here is position as a function of time. So again, I hope this looks familiar. Doesn't it look just like Calc 1 problems? Just be careful of the little landmines in that process. Okay. So on that, we're now done with section 12.5. Reminder: as we go through and complete sections of the book, I think it's a really good idea to go ahead and start on the homework exercises like as soon as you reasonably can, right? So it would, I don't know what your schedules are. Maybe go ahead and have lunch right after, right? But sometime pretty soon, early this afternoon, maybe go ahead and get started on section 12.5 exercises. The earlier you start them, the more closely it connects to things we've talked about in class, right? Strike while the iron is hot kind of a deal, sort of psychologically. And then, of course, you have more time to realize what it is you're having trouble with. Therefore, more time to seek out help, either in my office hours or the help room. Oh, is everybody aware of the help room? Show of hands. How many people know about the help room? Not everyone. Okay, so there exists this thing on campus called the help room. There's actually several help rooms for different courses. The Math 212 help room is shared with Math 202. And that help room meets 3 nights a week for 3 hours a night. It's staffed by students who have done very well in either this course or the more advanced version of it, Math 222, and are very often they're math majors. They're very strong mathematically. We screen them thoroughly, so you can get great help. All right, it's all free. 9 hours of free help per week. Right, evening hours, 7 to 10 p.m. So anyway, it's on. There's a link to it on our class website, so just click on the link to the full schedule. You can see who's going to be there. There's several staffers on each of the nights, and anyway, great resource. I encourage you to take advantage. Okay. All right. So as we move along a parametric curve, we're into section 12.6 now. As you move along a parametric curve, here's how differentials work. Again, I hope this is a familiar idea. I mean, we write dx dt as an alternative notation for x prime. Well, said differently there, your linear approximation dx of your change in position is x prime of t dt. And so here's the picture, there's your dx vector. And as the curve moves along, the parametric curve is like this. As you're moving along, well, I kind of missed there, didn't I? Here we go. Parametric curves moving along like that. dx represents the, it's not exactly the actual displacement in an amount of time dt, but it's your linear approximation based on the velocity that you were moving at that point. Dx is the sort of, assuming everything we're going along, with the same velocity over that amount of time, which of course it doesn't exactly. But it's just like the dy, right, in like a Calc 1 class. Okay. Anyway, easy formula for the differential. Don't forget x prime is v. So displacement is velocity times time. There's that old concept. Okay. The distance you've traveled then, now keep in mind we want to distinguish between the scalar concept of distance versus the vector concept of displacement. Displacement includes a direction. Right? Distance is just pull out the yardstick. How far is that? Right. Scale it. Okay, but that distance is just the magnitude of the displacement. It's the length of that displacement vector. By the way, a little bit of terminology. This vector here, different things you can call it. Very often, I'll call it the vector differential because it's the differential of this vector-valued function. You can also call it the displacement differential. You might more bluntly just pronounce it as dx vector. Right? That's all fine. Okay. But be aware you're going to hear me say vector differential, position differential, and that kind of thing. Okay. All right. Suppose you want to compute. Let's see. Can I fit all this? Yeah, there we go. Suppose you want to compute a distance along a parametric curve. How long is that little piece of parametric curve? Well, it's not x of t minus x of 0. X of t minus x of 0 would give you this vector. That vector is not a distance. It's not the magnitude of that blue vector. That's the, as the crow flies, distance. It's not what we're asking. I want to know, as my car drives along that road, how far is that drive, right? So that's a kind of a hard problem if you think about it. And the way we resolve that is we just observe that total distance, we're just adding up a bunch of little bits of distance, little differential distances. We're adding up a bunch of DS's, a bunch of little lengths, DS. And don't forget DS, I guess I do need this up here. DS is VDT. Everybody happy with that? Be careful with your notation. There's a little notational landmine here. This used to always creep me out when I was learning calculus for the first time, but it makes perfect sense if you think about it. And it was the why with the tau. Why do we have to get weird with our choice of symbols there? Why can't I just say V of t dt? And the thing is, we've already used t to represent the time at the endpoint, right? I've already made that choice. I want to know, how much total distance have I covered in a given amount of time, t. So t is the endpoint for this range of values of time. And so as such, if t is fixed, then as I move along, what is this thing that starts at 0 and ends at t? It can't be t, right? I mean, it doesn't make any sense at all to say consider values of t between 0 and t, right? Everybody see how that doesn't make any sense at all? So you just have to have a different dummy variable. The what you use in an integral, it's just a dummy variable. This, you could use q if you like. You could use, whatever. Suit yourself. Using tau here because it kind of looks like a T, sort of, and this is kind of representing, in some sense, the movement along this curve parameterized by time. So something that looks kind of like a T is satisfying, so we use tau. Anyway, that's all that's going on there. No big deal, but do be careful about it. Now let's talk about what is this v, little v. That's the magnitude of the velocity vector. So that's the speed, right? And the magnitude of the velocity vector is computed by the Pythagorean formula. Okay. All right. So that's all that's going on there. Okay. So we're going to get down and talk about curvature now. Curvature is a really interesting topic. There's some subtlety in talking about curvature. I mean, exactly what curvature is. I mean, let's just start with that. What is curvature? I mean, I think you guys have some sense of something. The way I have my fingers slightly bent there, not much curvature, right? If I do this, well, that's more curvature, right? There's more. Look at that's a lot of curvature going on there. So you understand less versus more. I think everyone's got an intuition, right? But how do we make that precise? What is, by definition, curvature? That's a bit of a hard problem, right? Now, for the purposes of this conversation, I like to visualize the curve in question as being a road. I don't know. I find this very satisfying. And then when we parameterize the curve, right, there's me, and I'm moving along with a certain velocity as I drive along this road. And I want to distinguish first between characteristics of the road itself versus characteristics of my process of driving along it. Right? So they're not the same thing. The road itself just sits there. I-40 has not moved in, I don't even know how many years, right? Probably 60, something like that, since they built it. That's a long time, right? But I drive real fast on I-40, right? So it's a very different thing. So we have to distinguish between, the way I like to say this, just for humor values, I've got to distinguish between the road and the road trip. Because it sounds vaguely, deep or something, right? So the road trip is the parameterization. Position as a function of time, right? If I'm moving along the road, my process, my road trip along that road is the parameterization. Okay. The road is this different thing. It just sits there. So the first thing we have to talk about is when we say curvature, don't conflate curvature with this experience that you have when you go real fast around a curve. The road takes a sharp left turn, and I can feel it's throwing me up against the right side of the seat. That's not curvature. That's something that's intrinsic to your process. If you drive really fast, you get a lot of whatever that is. If you drive really slow, you don't get very much at all. So that's not curvature. Everybody see what I'm talking about? Curvature is intrinsic to the road, not the road trip. Okay, so that's awkward because the algebra that we have, the way we describe roads is with a road trip, right? We parameterize the curve. That's our algebraic foot in the door to describe a curve. So we have a road trip given to us, and somehow from that we want to do something intrinsic to the road itself, independent of how I choose to drive on that road. Yeah, everybody see that? So make sure to keep this distinction in mind as we go through and talk about this stuff. So here's the definition that we're going to make for curvature, wherever I might happen to be. I guess guess I'll use the pencil. Wherever I might happen to be, there's a unit vector defining the direction that I'm going. It's easy to see by the way that unit vector is just the velocity vector divided by its own magnitude. It's the unit vector pointing in the direction of velocity. It's the unit vector pointing in the direction I'm going. Okay. That helps me define this angle, phi, and that phi is it's sort of it's a scalar. It's a single number that represents the direction that I'm going. And here's the idea. I want to know per unit distance traveled as I move along the road. As my distance changes, how does that angle change? And I appeal to your geometric intuition. Imagine a road where for every per unit distance as you move along the road, that direction is changing really fast. That's a lot of curvature. Right? On the other hand, imagine a different road where as you move along the road, per unit distance traveled along that road, the angle doesn't change much. That's would be not much curvature. So this relationship, d phi ds, gets our hands on the idea of curvature. Notice it's got nothing to do with time, right? I'm not saying rate of change of phi with respect to time. That's road trip stuff. That's you personally. That depends on how you drive. I-40 does not care how you drive, right? This is intrinsic to the road because that angle is intrinsic to the road, not how you got there. Distance is intrinsic to the road, not how fast you're driving. Okay. All right. So that's our definition of curvature that we're going to use here. And absolute value, by the way, in the same sense that distance is an intrinsically positive concept. We want to, in this context anyway, we want to view curvature as being an intrinsically positive concept. Okay, so Greek letter kappa to represent curvature. So here's some true facts. We're not going to derive this in this course, but it is derived in the book. If you want to read that, you can. It's a bunch of details. It's kind of cool, but it's not what I want to focus on. It's not what we as a course want to focus on. But if you parameterize a curve, this formula, all these derivatives are derivatives with respect to t. This formula will compute curvature for you. Now, I hope that some of y'all are a little uncomfortable with this formula after that whole speech that I gave about the difference between the road and the road trip, right? And notice that curvature is intrinsic to the road, while all of this stuff is intrinsic to the road trip. That should be a big worry. You should be thinking, whoa, how can you... The formula on the right in purple clearly depends on how fast you're going. Look, there's speed right there, right? Position as a function of time. We're taking derivatives with respect to time. That looks like road trip stuff. The amazing thing is that despite the fact that this is computed from the parameterization, this result will always be the same no matter what parameterization you use. So it's a way of getting our hands on this, again, this more abstract, thing, regarding the road itself from something that we can represent algebraically, namely parameterizations, aka road trips. Okay, so neat fact. Again, I'm not going to prove it here. What I do want you all to do is to be able to apply this formula. Make sure to know this formula, for one thing. And you can apply it in a couple of exercises. So here's one. If you have a circle of radius r, the curvature is 1 over r. It satisfies a sanity check, right? The bigger the radius, right? The bigger the radius, the smaller the curvature. Take that to an extreme. Look at the Earth itself. Curvature so low, people didn't notice, right? For a long time. Right? So this stands to reason, but how do we know it's 1 over r and not 1 over the square root of r or 1 over r cubed or something like that? How do we know it's exactly 1 over r? Well, the way you're going to do this is you're going to take this circle of radius r, you're going to parameterize it. Think about how you'd parameterize a circle of radius r. Right, look back into the section we talked about parameterizations and kind of rip off, from an example we did there, adapt it appropriately to this circle of radius r. With that parameterization, stick it into there, compute curvature, and out comes 1 over r. So it's a nice exercise. Everyone should make sure you can do that. Yeah?
Could you also say the change in angle is 2 pi and then over 2 pi r?
Well, no, that's a really interesting idea. You'd be making a case there about angle as a function of. It's true, but think of it this way: the purpose of this exercise is not to get to the answer. The purpose of this exercise is to make sure that you can use this formula. So for this purpose, let's go ahead and do it this way. But yeah, sure, you could make an argument along those lines. It's very clever. I like that. Yeah, but for here, let's use the formula. Okay, here's another argument, and I think this is a really nice one. Notice, and this is more important than it looks, this little trick right there, that is a parameterization. It gives position as a function of time, and it gives position as a function of time that traces out the graph y equals f of x. How about that? Now let's just observe why that's true. Well, x is t, and so, just immediately you can see here, y is indeed f of x, because x is t and y is f of t, as indicated. Really clever idea. I wish I'd thought of this. That was very cool. Anyway, so this is called the graph parameterization. Really good trick. We're going to use this a lot in Chapter 15. It's the most important trick that I'm aware of in terms of how to parameterize stuff. Anyway, this is our first experience with it, and I want you to use that to show that if you're looking at a graph curve, then this is the formula for curvature. Now, how are you going to check this? You're going to check this by first observing that parameterizes the curve in question, and we have a formula for curvature from a parameterization. You're going to plug in and confirm that you get this formula down here as a result. Okay, so nice exercise. Please make sure you can do that as well. It's a good little bit of mathematical weightlifting. Okay, some other facts that we're not going to prove. By the way, there's a bunch of stuff in 12.6 that is really interesting, but gosh, it's tedious. There's a lot of it, and we just, there's only so much time we have in the course, and so you're not responsible for the derivations of most of these formulas. You're not responsible for where this formula comes from. You're simply responsible for knowing that formula. Likewise, down here, a couple of other facts. Here's true facts that you don't need to know why they're true. But curvature can be reconceived as the magnitude of the rate of change of the t vector with respect to distance. Let me give you a very quick plausibility argument for that. If you think about it, angle and the unit tangent vector are just two different ways of representing direction. So in both of these formulas, the one at the top and the one at the bottom, both of them say what's the rate of change of direction with respect to distance. Just, conceived of differently, one as an angle, one as a unit tangent vector. But anyway, pretty plausible that would be true. More importantly, it is true. So make sure to know this fact. And another neat fact, this vector dt ds is always perpendicular to the direction of the curve. Weird, true fact. Okay, so let's go on to 3 dimensions. How are we going to define curvature for curves in R3? Got a curve moving along like that. I claim that going back to angles doesn't really make any sense. What angle, like if my velocity vector is like this, what angle represents that direction? This angle doesn't do it because there might be a little altitude on my, but what if I'm going that way, right? Is it just this angle that matters, or does this angle count? Do I add those up or something? I mean, what angle would we talk about taking the rate of change of? It doesn't really work to try to define curvature that way. But what you can do, this is not based on an angle. This is based on a vector, the unit tangent vector. and that extends just fine. Right, so this is our definition of curvature for a three-dimensional curve. And some calculations ensue in the same sense that it was in R2. dTds is always perpendicular to the unit tangent vector. Keep in mind we started off with velocity. Here, let me do it like this. Velocity was the first thing that we were talking about to define direction. dTds defines an orthogonal direction. We've decided to look at the unit vector pointing in the t direction. Kind of makes sense also then to talk about this unit vector pointing in the direction of dTds. And those vectors give a framework, we call it, for understanding this plane. This is what we call the plane of motion. So as you're moving along this parametric curve, as you're doing that, right, this is the direction that you're moving, and this is the direction you're sort of turning into. Right, so between your velocity and your acceleration, you're moving kind of within this plane. So you got to, if you think about it, I mean, if you're moving in a curve in space, you could be curving sort of like in an upward direction, or you could be curving in a horizontal direction, or you could be curving in some angled direction, right? There's going to be some sort of a plane that defines, at that particular moment, what is your, the direction that you're going and the direction you're curving into are both kind of describing the plane that you're moving inside of. So it's called the plane of motion. And this vector is called the principal unit normal vector. Principal unit normal vector. Just terminology. So acceleration, unsurprisingly. Let's see here. Acceleration is going to be some combination of those. When you're accelerating, think about how you drive in a car, right? As you're going around a turn in a car, you might be hitting the accelerator, right? But you're also turning. That's done with the steering wheel, not the accelerator. There's a couple of different kinds of accelerator. There's the acceleration that comes from changing your direction, and there's the acceleration that comes from changing your speed. These are different things. So this acceleration vector has components in each of these directions. There is what we call the tangential component of acceleration, and then there's what we call the normal component of acceleration. Right, at any given point in time, how you're accelerating, well, to some extent you're accelerating in the direction of motion, and to some extent you're accelerating perpendicular to that. Okay, so it turns out that all these things relate to curvature, and again, there's derivations here that you're not responsible for. We don't have time to go into this, but these are important players. So this thing, the tangential component of acceleration, make sure to know that formula. Good news, it's an easy formula, right? That's nice. Also, make sure to know the normal component of acceleration. Again, good news. It's an easy formula. So just make sure to know that formula. Where it comes from involves some tricky algebra that we just don't have time for. Is that yeah?
Is the normal vector pointing towards the center?
There is no center of the curve. I mean, the curve, keep in mind, is doing who knows what. And it's just that at this particular moment, you could say that, let's imagine temporarily that there is modeling the direction and sort of the nature of the curvature. You could talk about the circle, that it's as if you're sort of moving around some tilted circle. And then, the normal vector, the capital N vector is pointing to the center of that circle. But that's sort of a temporary, there is no actual center to the curve. Yeah. It's at a right angle from the tangent vector, but in an important way. The unit tangent vector, like that, there's a lot of different vectors that are perpendicular to that unit tangent vector, right? But only one of them is describing the direction that you're sort of curving into, right? There's this plane of motion. And only one vector is perpendicular and also parallel to the plane of motion.
Oh.
Yeah. Yep. Okay, so make sure to know these formulas, and through algebraic trickery that, again, you're not responsible for, this leads to a formula for curvature that you can compute from the parameterization. Make sure to know this formula as well. So here's the arguably four formulas that you need to know from this page. She had her hand up first. Go ahead.
What does the V in the formula stand for?
What is the what now?
Like the V.
Oh, this V right here?
Yeah.
Yeah, that's the speed. That's the magnitude of the velocity vector. Yep.
Is it on the picture?
It's the magnitude of the velocity vector. The velocity vector is like this, and so the magnitude is however far that is. Yeah, right. And you had a...
This basically answers my that, because I was wondering if A sub t measures speed or velocity.
So yeah, A sub t, so this is the extent to which you're accelerating in the direction that you're going. And if you think about it, if you have a certain velocity, and your velocity is like that, and my velocity is changing in the direction that I'm going, that is going to increase or decrease your speed, right? Whereas the normal component of acceleration, I mean, if your velocity is like that, and your velocity starts changing direction, right, the changing of the direction that you're moving comes from your velocity changing by an amount that's not in the same direction that it's going, right? As you can think of it, and it's not exactly rate of change of direction, but you can think of it that way. Yeah. Yes.
So you said there's only like one normal vector that points into the curve. Right?
Yeah, that's the principal unit normal vector. Yeah.
So is it like, are we going to be like able to like calculate? Find
Yeah, you can actually, and so that's a great question. So that comes from here. So the point is, you can compute this with that formula, and you can compute this with that formula, and we have long ago figured out how to compute that, right? And acceleration, that's just the second derivative, right? So everything in this formula, we have formulas that come straight out of the parameterization for everything in this big formula up here, except for that, which you can then solve for. Yeah. Yep. Okay. All right. So 12.6, we have kind of a weird treatment of 12.6. We want y'all to know these ideas about, what are these objects? What does normal component of acceleration represent? Right? What does that look like? How does it relate to these other objects? But the derivations of these formulas are quite tedious. The first time I taught this course, I went through all of it. And then they told me, like, right before the final exam, they're like, oh, yeah, by the way, we never ask students to know those derivations. And I was just like, I spent like 2.5 lectures going through all that stuff. So y'all are not responsible for the derivations of these formulas down here. You're simply responsible for knowing these formulas and for understanding, what these things look like in the geometric context as we've discussed them here. Okay. By the way, also in 12.6, there's a bunch of more material on planetary motion and Kepler's laws, and you're not responsible for that at all. Right? So, and I forget, it's like halfway through the section they start talking about planetary motion and Kepler's laws, and that's not any part of Math 212. It's very interesting, but it's not part of Math 212. Okay, so moving along, we're now into 12.7, I guess this is, surfaces in R3. This right here is just a compact way of saying an equation of three variables. I'll just make a quick observation. If you have an equation involving, three variables, x's, y's, and z's, right? There's an equation involving three variables. Notice that you could take all of that stuff and subtract it over to the other side, and you would have a function of x, y, and z equals 0. Right? So it's a little algebraic trickery, but it's convenient then to be able to say, anytime you're talking about an equation of three variables, we can talk about it in this form. Okay, so the question is, this is some sort of a surface in space, and how do I figure out what that is? Now, y'all have done a two-dimensional version of this, right? If you have an equation of two variables, that gives you a curve in the plane, An equation of 3 variables gives you a surface in space. Everything just jumps up one dimension. Right? So what we're looking for here is kind of a 3-dimensional version of stuff y'all studied in Algebra 2. Like, here's an algebraic curve. Here's an algebraic equation of x's and y's. Is it a parabola? Is it a hyperbola? Is it a line? Is it a what kind of thing is this? Okay. All right. So the one of the big tricks in answering these 3-dimensional questions is to find ways to connect them to 2-dimensional questions that we already know the answer to. It's a tried and true method in math to reduce a hard problem to an easier problem that we already have solved. So that's what we're going to do. So there's 2 methods for doing this that I'm going to show you. One is called cross sections, or the book calls these traces. To me, it's much more relatable to call this a cross section. So here's the idea. Let's look at this equation of 3 variables, right? Now, if I wanted to put it in the above form, I'd have to subtract over to the other side and have stuff equals 0, whatever. Okay, equation of 3 variables. I don't know what kind of wacky surface that might be, right? But there's algebra in the form of that equation, and then there's the surface, namely the set of solutions, that's a geometric thing that corresponds to it. Okay, and I understand the algebra, I see the algebra, don't understand this geometry. Okay, so here's the idea. This geometry that I don't understand, what if I were to take a cross-section of it? I mean, I don't know what it looks like, but if I were to take a cross-section of it, what would that look like algebraically? Well, that horizontal cross-section is that's the equation of a plane, right? If I want to understand this collection of points here that are that cross-section of this unknown blue surface, that collection of points is the collection of points that satisfy both. Let me say it this way. That red curve is the collection of points that are on the blue surface and simultaneously on the green surface. Now let me say that algebraically. This cross-section is the collection of points that satisfy the blue equation and that satisfy the green equation. And the thing is, that's really easy to write down, right? The collection of points that satisfy both of those equations, if x squared plus y squared is z, but if z is c, then x squared plus y squared is c. And notice 2 variables. I already know the answer to that question, right? I've reduced a 3 variable equation by way of a geometric concept. I've reduced a 3 variable question down to a 2 variable question, and that 2 variable question I already know the answer to. It's a circle. Notice I've drawn a circle there. And now that doesn't tell me the whole surface, but I know part of this surface now. Everybody on board? So this is called taking a cross section, or as the book would have you call it, the trace. I like cross section. And you can just keep doing this, right? The cross section, horizontal cross section down a little lower. That gives you a different equation of 2 variables, slightly smaller circle. And you can do this for as many planes as you want, and you can see what all these cross sections look like. And not surprisingly, if c is negative, if c is negative, there's no way x squared plus y squared could be negative, right? So there is no cross section there. But as long as c is positive, you keep getting these circles, and these circles keep getting bigger the higher up you go. Now, in what way? Is it like that, or what? To be determined. Okay, but we know a lot of information about this surface now. Is everybody on board? Okay, all right. Now, you can also take cross sections in other directions. So, what if we take cross sections perpendicular to the y-axis? In which case, y is a constant. Setting y equal to a constant gives you one of these equations. Now, what does that look like? Z is equal to x squared plus some constant squared. The lead being z equals x squared. right? Plus stuff. Okay, well, that's a parabola. Now, the plus stuff is that c squared. Z increases by c, so it's a shift up of our usual parabola by an amount c squared. Right? Keep in mind c is 1 in this case. So, however much you move to the right, however much your cross section is to the right, the square of that tells you how much the resulting parabolic cross section shifts up. So, I mean, again, applying this to a bunch of different cases, and you get cross sections that So this is sort of an upward shifted cross section. If y were 0, there's no upward shift at all. 0 squared is 0. If you're at y equals -1, well, c squared up, right? It's positive 1. And you get a bunch of different cross sections. Now, is this a beautiful picture? Does that totally tell me exactly what this surface is? No, not really. Right? But it helps. It's better than nothing. I know that what I had drawn previously is out of the question, right? I had previously drawn something like this that was kind of going up and kind of opening out, right? Clearly not. Look at these cross sections, right? So we've got more information. And, depending on how good you are at visualizing things geometrically, you can kind of piece it together and see what this surface looks like, one cross section at a time. Okay. And by the way, the answer is that this is a bowl called a paraboloid, and I'll be able to persuade you much more convincingly of why that is true next time, because we are out of time. So see y'all later. Have a good day. Have a good weekend.